Hello everybody, Mr. Hasty here. Today we're going to be doing section 12.2, which is on forces of attraction. What we mean by forces of attraction is that when you have two molecules, there are forces that pull them towards each other. So this actually leads to us having different states of matter. We're going to start with the question, why do different substances at room temperature exist in different states? So, real quick, if we're at 70 degrees Fahrenheit outside, then we know that O2 is a gas at standard temperatures and pressures. We know that H2O is water, is liquid. And we know that Fe iron is a solid. Why are they different phases at the same temperature? It has to do with the attractive nature of their molecules. So the O2 molecules floating around are not attracted enough to each other to form into a liquid state, like the H2O molecules are. The H2O stick closer together and thus form a liquid because the force of attraction between them is stronger. And things that are solid have an even stronger force of attraction that holds them together. Now, we've kind of hinted at these forces of attraction before when we talked about different types of bonds. So briefly, let's review the three types of bonds we've done this year. We started off talking about ionic bonds. Ionic bonds are where the bonding is done by a cation being attracted to an anion. Classic example, sodium chloride, table salt. So when you have sodium chloride, the molecules arrange themselves in this fashion. So that the positive sodiums are always next to the negative chlorides. And they build a little network in various geometries, and we looked at some of the crystal shapes and different geometries they form, but they are attracted in that fashion, and that is ionic bonding. Then we moved on to covalent. Covalent bonding is when two atoms decide to share an electron. So let's talk about this O2 gas. Basically what happens is they decide that they're going to share some of their electrons in between them. And the positive nucleus is attracted to those negative electrons, so it forms a bond and it's held together as O2 gas. Now, some covalent bonds are what we call non-polar. O2 is an example of a non-polar molecule, and some are polar. So what does that mean? Non-polar means they have a similar charge all the way around. So that they're either all neutral, all positive, all negative, all the way around. Whereas non-polar will end up having a positive side and a negative side, like water. If we look at water, I'm going to space this out here. If we look at water, we have oxygen gas combined with two hydrogens. Well, those hydrogens have positive charges, and the electron clouds that are left around the oxygen gas are going to have negative charges. So because we have positive on one side, negative on the other side, that's a polar molecule. And finally, we have metallic bonding, which is where metal atoms give up their electrons to what we call the electron sea, which forms a large negative region that the positive cations are then attracted to. So those are the three types of bonds. Now today we're primarily going to be focused on covalent nonpolar and covalent polar. We talk about forces of attractions. The ionic force that's attracting our ionic substances pretty much guarantees that unless we disassociate them in water, they're going to be a solid. And we already know that metals, except for mercury, are typically a solid. and that means that the forces there are strong enough to hold them in a solid form. So let's move forward into the different types of forces here. First, we're going to talk about dispersion forces. Dispersion forces are weak forces that occur due to changes in electron densities. So that's a lot to take in. Let's talk about what that means. So this most often happens in or I shouldn't say most often happens. This happens all the time, but it's more noticeable in nonpolar molecules. So here we have chlorine gas. Chlorine gas is nonpolar. The electrons on the ends make sure that it's kind of negative all the way around. But there they are sharing their electrons together, and that's what a covalent bond is. Now, what happens when two chlorine molecules get close to each other, like down here, these are electron clouds that are negative. And that means that they want to push against each other because they're the same charge. So what will happen is one of the molecules, it doesn't matter which one, will get some of their electrons pushed out of the way. So they'll push the electrons over to the other side of the molecule. And this will create a negative side and a positive side very temporarily. Now, the positive side is going to attract the electrons from this molecule, creating a attraction between the two, and that's a dispersion force. To disperse means to scatter. So as it disperses the electrons, then they attract to each other. And this is kind of a chain reaction, because if there's another molecule on the other side of this negative side here will push the electrons of the other one. So this can kind of create a kind of repeating effect. Now, these types of forces tend to be greater. So you have greater dispersion force if you have a greater size of molecule. And we can see this in the halogens. Fluorine 2 is a gas. Chlorine 2 is a gas. Bromine 2 is a liquid. And iodine 2 is a solid at room temperature. We worked with that before in the lab. So this is a gas, and then as the molecules get bigger, so remember, as we go down the periodic table, they get bigger, becomes a liquid, and then finally a solid. One last thing before we move forward, these positive, negative structures here have a name, and that's called a dipole. It means you have two poles that are oppositely charged. So we call this a temporary dipole because it's not permanent. It's not like in a water molecule where there's always the same positive and negative side. They could switch a little while later, but it creates a temporary time when one side is negative and one side is positive. So let's move on to the next type. Dipole-dipole forces. So dipole-dipole forces mean that we have dipoles in two different molecules and that they are attracted to each other. So they are the attraction of oppositely charged poles. Now, we're going to talk about water a little bit later. So I picked a molecule this is nitrous oxide. Or more properly said, the nomenclature is dinitrogen oxide, but it's more commonly referred to as nitrous oxide or laughing gas. So when you have this molecule, remember red is oxygen. So these are negatively charged, and they actually develop a positive charge right here. So they create a pole. Now, this guy, the guy on the end, is neutrally charged, so he's not gonna have a charge. So I'm going to actually move these diagrams around here. I'm going to clear out what I drew there and move these diagrams around to show you how they're going to attract to each other. Now, I had to clear out my drawing. So remember, the red side is positive and the blue middle, or sorry, the red side is negative and the blue middle is positive. So how these would align would, if we had one molecule here, this red negative one wants to attach that positive middle one. So it'll rotate and fit into form, and these don't overlap real well. So let's do it like that. And this positive right here is attracted to this negative. And they'll kind of hold like that. And the next one, the red would be here. That's our negative, positive here. And then our neutral over here. And then the next one would be negative here to the positive. And they build a structure like that. So dipole-dipole, where one dipolar, meaning has two poles, is attracted to another, and they form these kind of structures. Now, generally, when we talk about forces, we want to know which ones are stronger. Are dipole-dipole forces stronger, or are dispersion forces, which we just learned about, stronger? Well, generally for small polar molecules, dipole-dipole can be greater than dispersion. But for most, once you get up to a decent size, and that's kind of like, there's a lot of factors here, but most polar molecules, dispersion forces are greater than dipole-dipole. So you have to be real small with very particular qualities for that to be true. All right, let's move on to the last one. All right, so now we're going to talk about hydrogen bonds. Hydrogen bonds are a type of dipole-dipole bonding. So they are dipole-dipole bonds formed by molecules containing hydrogen and small, highly electronegative atoms. So generally these occur when you have hydrogen and oxygen. So when we say small, very highly electronegative atoms, that will include oxygen, nitrogen, and fluorine. So, how do they work? Well, because the hydrogen, if you remember what a hydrogen atom looks like, it looks like one proton and one electron flying around the outside. So when that electron bonds with the oxygen, it doesn't leave any electrons on the end. This side of the molecule is pretty much all positive hydrogen nucleus. So it means that it's going to be rather strongly positive, and this side is going to be rather strongly negative. So what happens is your H2Os, and we talked about this before, tend to form structures where the hydrogens are attracted to the oxygen ends. And this leads to a lot of the properties that water has, a lot of how it crystallizes when you make ice and things like that. So, how do these compare to the other types? Well, remember, hydrogen bonds are a special type of dipole-dipole, but they are actually the strongest of the types of bonds we talked about. So, if we put them in order, hydrogen is probably the strongest, followed by dispersion for anything that's not real small. And then we have a dipole-dipole as our final in terms of what the order of strength is. So the differences lead to a lot of different properties. For instance, hydrogen has hydrogen bonds are very strong. So let's take water as an example. Water freezes at 0 degrees Celsius. Here, let me clear some of this. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. But if we take something like methane, remember, is CH4. It is nonpolar. It's just talking dispersion forces. There's no dipole-dipole. There's no hydrogen bonding there. It boils at negative 161.5 degrees Celsius. And to freeze it, we'd have to go even lower than that, so way lower than 0. And ammonia, for instance, is at negative 33 degrees Celsius. Remember, ammonia is NH3. And so it's going to be hydrogen bonded as well. So things with hydrogen bonds tend to hold together much, much better. I put these on the wrong side. Actually, I didn't flip them. But NH3 is going to have polar bonding as well. Hydrogen bonds as well. So why is it so much lower for a boiling point than water? And that comes from the fact that oxygen is a lot more electronegative than nitrogen. And because the key component there is what they're bonded with to decide, part of the equation is the hydrogen. The other part is the element they're bonded to and how electronegative that is. All right. So quick review. 3 types. We have dispersion forces, which are weak forces created by temporary poles that are formed. Dipole-dipole forces, which is where something is naturally a dipole and the positive and negative ends are attracted to each other. And hydrogen bonds, which are a special case of dipole-dipole, because hydrogen and really small electronegative elements make really, really strong poles. Really, really positive and really, really negative poles. All right, guys, that's it for today. See you next time.